Let's solve problem 8 on the 2023 AIME II. So the problem says let W equal cosine 2 pi over 7 plus I times sine of 2 pi over 7, and we're asked to find this product. Okay, so first let's understand this notation, right? This is going to iteratively go from k equals 0 to k equals 6, and what we're essentially doing is we're just multiplying this product over and over again. So for k equals 0, we'll have w to the 0 plus w to the 0 plus 1, so that's just going to be 3 for the first term. For k equals 1, we'll have w to the third plus w plus 1, and etc. all the way until k equals 6, where we'll have w to the 18 plus w to the 6 plus w plus 1. So this is the product that we need to find. Now, it looks pretty complicated, right? Because how are we supposed to deal with this cosine and sine stuff? And we can't really bash it out. That's going to take way too much time. Well, let's first kind of relate this to Euler's formula maybe, right? Because it's in the format of cosine plus I sine. So Euler's formula tells us that any complex number can be written as re to the power of I theta, which is r times cosine theta plus I sine theta. Here we see that w is just going to be equal to e to the power of 2 pi I over 7. Okay, so what does this mean exactly, right? Well, by Euler's formula, one thing is very obvious, right? What's 1 going to be using Euler's formula? Well, 1 is just going to be equal to e to the power of 2 pi I, right? Because cosine of 2 pi is 1 and sine of 2 pi is 0. So 1 is e to the power of 2 pi I. So w is actually just the 7th root of 1. So we can say that w is a solution to the polynomial c to the 7 minus 1 equals 0, right? It's one of the solutions. So what are the other solutions? Well, let's think of the other solutions, right? So 1 can also be written as e to the power of 4 pi I, right? It's the same thing, because anytime we add 2 pi I, the angle doesn't change really. The cosine and sine don't change. So then another solution could be e to the power of 4 pi I over 7. In fact, we can even write 1 as e to the 0. So another solution could just be e to the 0 over 7, which is just e to the 0. And we can keep doing this, right? E to the 0, e to the power of 2 pi I, 4 pi I, 6 pi I, 8 pi I. So when is this going to stop? Does it ever stop? Well, a polynomial is e to the 7 minus 1 equals 0. It has a 7th degree. So it can have at most 7 distinct roots. So that means that the roots to this polynomial are, we can have at most 7 of them, right? And after that, this is just going to start repeating. So I'll show you what I mean. So the first solution is just going to be w to the 0, which is 1. Also e to the 0. W to the 0 is basically e to the 0. W is basically e to the power of 2 pi I over 7, right? W squared is e to the power of 4 pi I over 7. W cubed is e to the power of 6 pi I over 7, etc. Now, when is this going to stop? Well, when we reach w to the 6, which is 18 pi over 7, then we have to stop, because w to the 7 is going to be e to the power of 14 pi I over 7. But that's the same thing as e to the power of 2 pi I, which is already equal to 1, which is basically the same thing as w to the 7. So this is basically the root. We call these roots of unity, right? These are the 7th roots of unity, so the 7th roots of 1, all the complex 7th roots of 1. And in nature, these 7th roots of unity are cyclic. So that means w to the 7 will be w to the 0, w to the 8th will be w to the 9 will be w squared, and you can even prove this yourself, right? If you want, let's say w to the 9, why is w to the 9 equal to w squared? Well, let's just plug everything into Euler's formula, right? So if we take w to the 9, right, that's basically going to be e to the power of 2 pi I over 7, which we already established to be equal to the w to the power of 9, which is e to the power of 18 pi I over 7. But we can always subtract 2 pi, right? That's just 360 degrees, and it doesn't ever affect sine and cosine. So if we subtract 14 pi, then we just get e to the power of 4 pi I over 7. And if you notice, this is exactly the same thing as w squared. So that's why these roots of unity are cyclic in nature. But okay, I kind of like got a bit off track here from the problem, but this is going to be very useful for us. So now with this valuable information, right, let's write out our product. So the product is, I'll just write it out for a sec. Okay, so this is the product we need to find, right? Now, immediately we see that that cyclic nature thing really comes in handy here, because now we can take all these really big powers and just convert them into small powers. So how are we going to do that? Well, we can kind of notice a pattern, right? Like w to the 9 equals w squared, and these have a difference of 7. So let's see what does. So w to the 15, that's gonna have a difference of a multiple of 7, right? So w to the 15, the closest multiple of 7 is 14, so 15 minus 1 is 14. So w to the 15 is equal to w to the 1, which is the same thing as w, right? So we can replace this with w. And we can do the same thing with all the other large exponents. W to the 9 is just w squared, because 9 minus 2 is 7. So we'll take this, and then we'll do w squared. And then w to the 12, we can do as w to the 5th. So, and then finally, we can have w to the 18th equals w to the 4th. So now the product is still complicated, but not as complicated as before. So now the really, oh wait, this is a plus sign. So the main thing that we really need to do here is not evaluate all of this at once, but rather evaluate this product like in pairs. So we'll take two terms, and then we'll take that product and see if we notice a pattern. But which two terms should we choose, right? Because we can choose so many pairs. Well, note that w to the 7 is the same thing as w to the 0, right? And that's just equal to 1. So we really want to deal with as many of these as possible. We want 7 as much as possible because we can just automatically convert those to 1. So where can we find 7? Well, the first place we can look at is w to the third. Oh wait, w to the third. And then we want a corresponding w to the fourth somewhere. We can find that here, right? And the cool thing is we also have this w to the 6 and w here, so we'll have even more w to the 7s than if we just chose this option, because w to the 5 times w is w to the 6, and that has less w to the 7s than this. So let's maybe take the product of this term and this term. So if we do that, then we get 1 plus w cubed times 1 plus w to the 4th plus w to the 6th. Okay, and then let's just expand this out. So then we're basically going to get 1 plus w cubed plus w to the 4th plus w to the 5th plus w to the 7, which is just 1, plus w to the 6 plus w to the 7 again, which is just 1, plus w to the 9, which is w squared. Okay, so now we have 1, 1, 1, and then we have this increasing sum, w plus w squared plus w third, w fourth, w fifth, w sixth. Okay, so how do we find this sum? Well, remember what I mentioned earlier. All of these are solutions to the polynomial z to the 7 minus 1 equals 0. And this is just like any other polynomial, so we can utilize Vieta's formulas. So we can say 1 plus w squared plus w cubed plus all the way to w to the 6 is going to be equal to 0, because the negative, right, by Vieta's, that's just going to be equal to 0. So that means w plus w squared plus w cubed plus all the way to w to the 6 is just 0 minus 1, because we're excluding the 1. So this is just evaluates to negative 1. So all the w's here, these just evaluate to negative 1. So 3 minus 1 just makes this equal to 2. And we see we basically get 2 for all of these other pairs, right? If we took 1 plus w squared plus w to the 6th times 1 plus w to the 5th, then we're also going to get 2. And if we finally take 1 plus w squared plus w cubed and multiply that with 1 plus w to the 4th plus w to the 5th, then we'll also get 2. So really, our answer is just going to be 3 times 2 cubed. And 3 times 2 cubed is just 3 times 8, and that's just going to be 24. So 24 is the final answer for this problem.